All right, nerds, today we are going to cover Unit 1.1-B. I guess you can, it's the second part of 1.1, okay? And today we're going to talk more about how things are changing. Yesterday specifically we talked about slopes and increasing, decreasing, constant, right? So that was how are the y's changing as the x's are changing. And that's one of the reasons why it's called change in tandem. So it's all about how is one thing changing and another is changing. Yesterday, if the y's were going up as the x's were going up, increasing. If the y's were going down as the x's were going up, decreasing. And if the y's were unchanged as the x's were going up, constant. Today, we're going to discuss types of curvature. Let's say it like that. So yesterday was types of slopes. Positive slopes is increasing, negative slopes is decreasing, zero slope is constant. Today we're going to discuss types of curvatures. It's called concavity. So this is the types of curvatures that we have, and some things called inflection points. An inflection point is where a curve changes from concave up to concave down, or of course you could say concave down to concave up. Now, if you want to be able to find your points of concavity algebraically, you need calculus. You'll learn how to do that next year in AP Calculus. However, if you're looking at the images, it's not that bad. This is what concave up looks like. It's like bullhorns shaped, pointing up, concave up. So there's actually two types of concave up, and they kind of showed you two, but what I want to show you is it could look like this or this. These are both concave up. Now, yesterday we discussed rates of change, slopes, increasing, decreasing, constant. Both of these are concave up. However, for this one, if you were going from left to right, your roller coaster's coming down. This one is decreasing and concave up. Whereas this one, if you were riding the roller coaster, you'd be going up. This one's increasing while being concave up. So it's important that you understand that concave up actually doesn't tell you anything about increasing or decreasing. It just tells you that the curve is literally curved upwards, like bullhorns or like a bowl. And it could be either up and to the left or up and to the right. This is a big deal for AP. You need to know that if something is concave up, that means that the rate of change is increasing. Not the curve is increasing. This curve is increasing. The rate of change is increasing. This means your slopes are getting bigger. If your slope values or your average rates of change, so I know it says rates of change, but that could also mean average rates of change. If your rates of change or average rates of change are increasing, that means your curve is concave up, one of these two shapes. And I could demonstrate that for you using straight lines. Let's see. If I connect these two dots, I'm hoping you can see that that is a positive slope. Yes? But if you had to give it a fractional value, it's probably like, 1/6 or something like that. It's a very shallow positive slope, right? Now, if I went from here to here, I still have a positive slope. But now it's closer to a slope of 1. It went up from, say, a 1/6 to a 1. And I could also go from here to here, connect two dots on here, and try to calculate the average rate of change, because that's all the average rate of change is. It's the slope between two random points. This slope would be like +2. So I'm hoping you could see with those values, and I'm estimating maybe 1/6 of a slope. I'm estimating maybe a slope of 1. And estimating maybe a slope of 2, But look at the numbers, 1/6, 1, 2. They're clearly going up from left to right. So we could say that the slopes are growing. We could say the rate of change is increasing. We could say the average rate of change is increasing, because I could have done this point to here, this point to here, this point to here, and every single time my average rate of change would have gotten larger. So I could also say that. Concave down is like you took a piece of rebar and we're trying to bend it like a strong man straight down. It's curved downwards. And just like there are two types of concave up, there are two types of concave down. You could have down and to the left, or you could have down and to the right. Again, concavity doesn't tell you anything about increasing or decreasing. It just tells you which way it's curved. This is concave down, but this roller coaster would be increasing. From left to right, it's going up. This is also concave down, but this roller coaster would be falling down from left to right, so it's decreasing. So we just need to know there are two different types of concave up, there are two different types of concave down. And if your slopes getting larger is showing you that you're concave up, I hope it's obvious why your slopes getting smaller is concave down. So you can say the rate of change is decreasing, or you can say the average rate of change is decreasing. This one, I didn't do average rate of change from the beginning dot. This one I will, just to show you that it doesn't matter. So I could have this blue line with a negative slope. I don't know, negative 1/6, 1/8, whatever, I don't know. It doesn't matter. The point is it's really shallow. Then I could connect the first dot and the second dot. This is an average rate of change. I'm hoping you see the slope is still negative, but it's even more negative, if you want to talk about it like that. Falling faster. I don't know, -1? Just estimating. This is an average rate of change. I took two random points on a curve. Another average rate of change. Let's see, I'm going to turn my paper sideways to hit this one. Even more negative. I don't know, let's say that one's about -2. Do you see that these numbers are decreasing? -1/6, then -1, then -2. The further negative you get, further negative, that's a number decreasing. You're getting smaller. -2 is smaller than -1. So do you have any questions about how it looks and it's related to concavity? Or how we can talk about rate of change while talking about the rate of change changing? It's a weird thing to say, the rate of change changing, but it can. No? Okay. And again, if you ever change from concave up to concave down or vice versa, that point that you found is called an inflection point. We will use interval notation to describe zones of concave up, and we will use interval notation to describe zones of concave down, just like we did for describing zones of increasing and decreasing. However, remember how we said when we're changing between increasing, decreasing, and constant, we use brackets? When we're changing between concavities at inflection points, we do not use brackets. Why? There's a calculus reason why, but you have to understand calculus to know why. So here we have a graph, and we've been given all of our xy's that are going to be important to us for this question. Use this graph to find intervals where we have this going on. So first, let's look for increasing. Increasing is going to be where our roller coaster is rising. What would be the very first x where we start rising? -3. So we're going to begin increasing at -3. Where would we stop increasing? What x? 2. Good. That is not the last time we're increasing, so union. The last time that we're going to be increasing begins at which x value? Lots of people can shout it out, you know. 4 is it. We will never stop increasing after x equals 4. So for all infinity to the right. So going up, going up. Decreasing. This is where we start, quote unquote, decreasing to the far left. So we'll describe that with negative infinity. And I hope it's obvious that since this was the x value where we began increasing, this is the x value where we end decreasing. Remember, increasing, decreasing changes always get brackets. It's not the only time our roller coaster is decreasing. I hope that's obvious that because I stopped increasing at x equals 2, that's where I started decreasing. And if 4 is where I began increasing, 4 must have been where I stopped decreasing. This curve does not have any intervals of constant rate of change. No flat zones. So where is it concave up is the question. Okay, you might have noticed that there are some points that we didn't talk about. I just kind of ignored them, right? One of those points is right here. And another one of those points is right here. I have cut this graph into 3 large zones. And those 3 large zones are showing me my concavity zones. Everything to the left of that red dotted line is concave up. Everything between these 2 dotted lines is concave down. And everything to the right of this red dotted line is concave up again. Again, how would you know where to find the inflection point? Well, you need calculus, or you need the graph to make it obvious. And worst case scenario, if you're asked to estimate where it is, you could just take the average of these 2 x's. So go the average between a maximum and a minimum. That's a good estimate for an inflection point. Is that where it always is? No. But without calculus, that's the best you can do. Either the picture makes it clear with a dot, or you would find the average between the maximum and minimum x values. Okay? Okay. So where are we concave up? Out here, negative infinity to there, negative 0.5. Concavity does not get brackets. And we're also concave up to the right of x equals 3. For all infinity. You okay with that? If you guys aren't, please say something to me. I don't want to rush this. It's a big deal. Change in tandem, rates of change, and concavity are something that we will talk about all year. It kind of like is the underpinning of the entire program, is understanding how functions and graphs change with themselves, like how the y's change with the x's, and how the rates of change with the x's. Okay? Yes, ma'am, Grace.
Why did you only use x's?
So when we talk about where things are occurring, Onyx, she wants to know why I'm only using the x's for my intervals. When we talk about where things are occurring on functions, we say they're occurring across x values. So where is your maximum? Oh, there's a maximum at x equals 2. Where is your minimum? Oh, there's a minimum at x equals negative 3. Where is this graph decreasing? To the left of x equals negative 3. Now if you say, what is your maximum value? 2. What is your minimum value? 8. So the only time that you are going to use your y values for any intervals is the range. Otherwise, we're talking x's only. You might have noticed there are no y values or x values on this graph, right? In IB mathematics and things like that, and even in calculus next year, you're going to do a lot of sketches like this where all you really cared about was the x's, and you go, how far down does this bump go? You can say, I don't know and I don't care. How far up does this bump go? I don't know and I don't care. It's just where did it occur? Oh, it occurred at this x value. Okay. Yep.
Why is the maximum 2 when it's not?
We haven't talked about maximums and minimums yet. It's going to happen in today's lesson. Okay. It doesn't mean, when you say maximum, it doesn't mean the highest point across the entire thing. It doesn't mean that, which we'll talk about somewhere. Maybe not today's lessons, maybe tomorrow's lesson. It is coming up though, I promise. Yes?
Why wouldn't the concavity get brackets?
Why does, I think the real question is why does increasing, decreasing constant get brackets? See, when I took calculus and with my math degree, I firmly believe that brackets here on increasing, decreasing constant are inappropriate. My knowledge of calculus tells me that right here at this point, I am neither decreasing nor increasing. So I would have always used parentheses, and that's what Ms. Bluebaum, one of our AP calculus teachers, that's what she was taught, and that's how she believes as well. We're teaching what College Board has changed their minds, and they have recently decided increasing, decreasing constant gets brackets. I can tell you, calculus-wise, remember I've mentioned slopes. Every one of these slopes is negative. Every one of these slopes is positive. The slope at this point is 0. And 0 is neither positive nor negative, so I don't like brackets. But I have to make sure you're getting questions right on the AP exam. And here, when we're talking about concavity, in calculus you'll learn, concavity is actually the slope of the slope. You'll learn about it when you learn some calculus. It'll make a lot more sense about what I just said. And right here, the slope of the slope is 0, neither positive nor negative. That's why it gets parentheses, because it's 0. But for some reason, that logic, College Board has decided, doesn't fit here. I don't know. Maybe they're just being extra. So I guess the best answer to your question is, I have no idea why we use brackets here and not here. Because in my opinion, brackets is wrong completely. But I got to make sure you get questions right. So, increasing, decreasing constant, brackets. Concavity, no. I know, that sucks. I'm sorry. I hate it too. So let's look at our graph. And let's see, when were we increasing and concave up? Well, here's some concave up. Is there a portion of this that was increasing? Yes, there was. From -3 to -0.5.
Wouldn't it be -3 to 2?
No, because from here to here, we're concave down. Okay? So the red lines are where the concavity has changed. So right here, in this zone only, up to the left, obviously, that's increasing and concave up. And because we're using concavity, I'm not going to use brackets. And the other zone where we are increasing and concave up is over here, to the right of 4. So the only place where my graph is concave down is between these two red dotted lines. So from x equals -0.5 to x equals 3. When is it concave down and decreasing? Right there, itty bitty. So from x equals 2 to x equals 3. So on this graph, we have decreasing concave up, increasing up, concave up, increasing concave down, decreasing concave down, decreasing concave up, increasing concave up, increasing, decreasing, concavity, completely separate ideas. More questions on rate of change or rate of change changing? I'm gonna be real with you. This kind of stuff will make more sense once you know calculus. You'll be able to look back on that and go, oh yeah, okay, that kind of shaky understanding I had, now it's cement. With a little bit of calculus knowledge. A little bit, won't take much. Alrighty, well if nobody is panicked and freaked out about, oh, Ian, yes?
How come 3 to 4 isn't decreasing and concave?
So from x equals 3 to x equals 4 is decreasing, yes, but it's concave up because it's bowl-shaped, like bull horns. So when it's bull horns, it's concave up, okay? So where are my inflection points, which I didn't ask? I'll write IPs. The inflection points are going to happen here at x equals negative 0.5 and at x equals 3. So that is where your concavity changes between the two. Yeah, Caroline, what's up?
On the test, are you going to have us find the inflection points with the averages of
You may need to, yes. You need to be able to do both. So you'll need to be able to identify them by looking at the graph, if there's a point there, obviously. And you'll also need to be able to estimate them by finding the average between an x where there's a top of a bump and an x where there's a bottom of a bump. Known as minimums and maximums, okay? And we'll talk more about minimums and maximums in a later lesson. Okay, old material intercepts, right? X-intercepts, that's a place where your graph crosses the x-axis. But if you're on the x-axis, what is always true for every single graph? No matter what, if you're on the x-axis, what's always true? Y equals 0. And the y-intercept, that's where you cross the y-axis. And no matter what, for every single graph, if you're on the y-axis, what's always true? X is 0. So if you ever want to find a y-intercept, very simple, just substitute in x equals 0. Because x equals 0 puts you on the y-axis. Now, often finding the x-intercepts is a little more difficult. I mean, yeah, you set the whole thing equal to 0, but it's usually going to either involve a calculator or factoring. So it says, name the intercepts. Okay, well, x-intercepts. I see one here. One here. One here. Y-intercept. Quick understanding question for you. Can a graph of a function ever have more than one y-intercept?
No.
Trying to remember names. I don't want to say the wrong name, but what's your name? I should have said Logan. I knew it was Logan. You were quick. You shook your head. No. Why?
Then I wouldn't follow that rule.
What the rule that you're making with your arm? What's that rule called? The vertical line test. Awesome. Good. Yeah, if you have more than one y-intercept, you'd be failing the vertical line test, which means you don't have a function. Perfect. Good. I know that's not part of the lesson, just, tying stuff together. This one says to find the intercepts algebraically. We're going to have to factor. Since it has 4 terms, we're going to have to factor it by grouping. We talked about that in the prereq review, correct or no?
Yes.
I know I did with my algebra 2. I couldn't remember if it was on yours as well. Factoring by grouping. So in this first group, we look for our GCF. I see that they have x squared in common. And in this group, notice I was careful to capture this minus sign. It's part of the 4. And since this thing begins with a negative value, my GCF is negative. Negative 4. I could factor off the x minus 3. And from the left thing, I'm left with x squared. From the right thing, I'm left with minus 4. This factors. This is a special case. This is a squared minus b squared. The difference of two squares will factor to a plus b, a minus b. So x plus 2, x minus 2. I know I changed the order of my parentheses. That doesn't matter. Be looking for the zeros of this. So this is me trying to find my x-intercepts if I set the thing equal to 0. My x-intercepts, well, they're going to be just whatever makes the inside equal 0. Negative 2, positive 2, positive 3. So it's factoring by grouping. Old material. Towards the beginning of Algebra 2. Maybe even Algebra 1, I'm not sure, I don't remember, it's been a long time. That's just the x-intercepts. What about the y-intercept? Well, plug in a 0 for x. What are you going to get? Let's look at the equation. What do you get if you plug in a 0 for x? 12, right here. For any polynomial, the constant at the end will always be your y-intercept because everything else will have an x with it. Easy peasy lemon squeezy. Do you need to ask me any questions about finding intercepts? Yes, sir.
For the x-intercept, did you say plus or minus 2 and 3?
Yeah, plus or minus 2, comma 3, that'll work too. Which you also could have found here if you had just said x squared minus 4 equals 0, add 4 and take the square root of both sides. You just have to remember that when you cancel a square with the square root, you get a plus or minus. But because a lot of people forget it, I'm in the habit of just factoring. But yeah, you could have just said plus or minus 2 here. It's fine. Okay. Tina is a sales clerk at Electronics Depot who earns $325 base pay plus $18 for each item sold. Express her gross salary, G, as a function of the number X of items sold. Find her gross pay if she sells 24 items. So basically, write an equation and then use the equation to find something. So it says her gross salary is G. Gross. She has a base pay of $325. That means no matter what, regardless of how many items she sells, she's going to make the 325. Should I put an X next to this 325? No. And the reason why is because this is independent of the number of items we sold. Doesn't matter. Plus 18 each or per item. If you see a word like each or per, that means you were dealing with a slope, a rate of change. That goes in front of a variable. There it is. $325 a week and $18 per item. There it is. Find her gross pay if she sells 24 items. Plug in 24. Make it green for money. 325 plus 18 times 24. No, I'm not going to try to flex. I don't know what 18 times 24 is off the top of my head. But in 8th period, I'm going to look like a genius when I go, and everybody should know, and I'll just say what the answer is. 757. This is money. Make sure you use your units. If you don't use units, you will not get the mark for the answer being correct in your free response questions. You must use units for AP classes. if you had one, if your pre-calculus textbook is dropped from a height of 45 feet on the planet Newton, its height in feet after t seconds is approximately this equation. Height after t amount of time is 45 minus 14t squared. How long does it take for the book to hit the surface of the planet? I guess the real question is, if the book is hitting the surface of the planet, what is the height then? What's the height of my pin from the table? 0. So if it hits the surface, the height is 0. So we're just getting t by itself. Add t to both sides. Take the square root of both sides. Technically, there should be a plus or minus, except for, well, time travel has not been invented yet, so we're not going to worry about negative time. I don't know what the square root of 45 is, but I do know it's a little bit less than 7.
Wouldn't it be 45 minus 14t squared?
Did I miss some equation? Oh, well, I wish you'd have said something long before I grabbed the calculator and everything. I forgot to write the 14. Add the 14t squared to both sides. Divide by 14. You guys could say something. And then take the square root. All right, let's try that again. Now, for AP classrooms, AP classes, I should say, round to 3 decimals, always. Unless it's less than that, like let's say it stops at 2 decimals, or unless the directions have told you to do otherwise, we round to 3 decimals. And if you use less than 3 decimals, your answer will be wrong. It will be marked as wrong. So to 3 decimals, this is 1.793 seconds. No, you do not have to have the approximation symbol. Because they expect you to round to 3 decimals. Got a couple different graphs here. We got an f of x and a g of x. F of x is this one that's parabola, then flat, then downwards. G of x is a bunch of positive slope, negative slope, positive slope, a bunch of straight lines. So we're going to use this image to answer the rest of this page. First, the domain of each function. F of x. Double arrows. What's that domain then? All real numbers. G of x. Double arrows, same thing. All real numbers. It's the same for both. Part B says, when is f of x 0? That means when is f of x on the x-axis? I see that happening here, and here, and well, that's it. So at -4 and +2. When is g of x 0? Here, here, and here. Looks to me like it's at -2, 5, and 7. Question C says, when are they equal to each other? Oh, well, when 2 graphs are equal to each other, they're intersecting one another. So that's happening here, and once again, here. And the when is looking for the x values only. So here I have x equals -3, and here I have x equals +3. Oh, missed one. Bless you. X equals +9 also works. So -3, +3, +9. And Barry, just for you, we'll do plus or minus 3 and a 9. There you go. Part D says when is f of x greater than g of x, and that means the y values. So literally, looking at the picture, when is the graph of f above the graph of g? The orange dots are going to be my barriers. So to the left of this orange dot, I hope it's obvious that f is above. And between these two dots, f is above again. So I have to the left of -3, and since this doesn't have an equal to bar, I can't put a bracket on this 3, -3, and also from +3 to +9. That means all the other zones, other than these two, are places where f of x is below, less than g of x, which is what this one's asking for. So here, from -3 to +3, f of x is less than g of x. As well as out here after the number +9. And again, if we had had an equal to bar on either of these symbols, then I could have used a bracket. When is g of x greater than 0? Well, we've already identified when g of x equals 0. So what we have to do is look at when it's greater than 0. So look at my green dots. I see greater than 0 between these two. So from -2 to +5. And after this green dot, so after 7. When is f of x negative? When's it below 0? Well, we used our purple dots to show us when it's equal to 0. Looks like it's only below 0 from -4 to 2. This little curvy zone right here, from -4 to 2. That looks like a coordinate, doesn't it? It's not, through context. Because it's talking about values of x, we know that this is a string of x numbers. Alrighty, now it wants to know when x is increasing. Not x, excuse me, I said the wrong letter, f. When f is increasing. We can identify zones of increase, decreasing change. I hope pretty easily just by looking for when roller coaster is going up and down. We're only looking at f though. So here is a place where it changes. Here is a place where it changes, which is not even a whole number, unfortunately. And here is a place where it changes. Increasing, when your roller coaster is going up. Looks to me like it's from here to here. We'll call that, what, 3.5? So -1 to 3.5. Increasing, decreasing always gets brackets. -1 to 3.5. Constant. Yeah, f of x has that flat part right here at 3.5, and it comes to an end right here at 6. When is g of x decreasing? All right, let's take a spin on g of x. Let's see. Increase, increase, from here to here is decrease. The only time. So from x equals 3 to x equals 6, increasing, decreasing, always gets brackets. We've already done part G, and it asks where is f of x below 0. So when we go to do part K, when it says where is f of x above 0, it's everywhere except for here. Everywhere else. So we could say from negative infinity to negative 4. And then once again, from 2 to infinity. It's the entire number line except for this span of numbers. And lastly, to wrap up section 1.1, when is f of x decreasing? When is our roller coaster going down for f of x? Looks to me like to the left of the first blue circle, so negative infinity to negative 1. Increasing, decreasing always gets a bracket. And after 6, there it is. Oop, couldn't see it on the screen. I hope that you found it palatable at least.